January 31st, 1943. A Luftwaffe radar station near Emden, northern Germany. Obergefreiter Klaus Richter watched the Würzburg radar display as the green phosphor trace swept across the screen. Standard night patrol. German radar operators had tracked every RAF bomber entering Reich airspace for 2 years. They knew the signatures: slow-moving Lancasters, laboring Halifaxes, the distinctive profiles of British heavy bombers crossing at altitude. The radar painted clear images. Metal airframes reflected radio waves reliably. The system worked. But tonight's trace looked wrong. Something was crossing German airspace at high altitude, moving faster than any bomber Richter had tracked before. The radar echo flickered weakly, barely visible against background noise. He checked his equipment. The Würzburg was functioning normally. Other targets painted clearly, but this contact appeared and disappeared, its radar cross-section too small for an aircraft moving at that speed. Richter called the observation. Ground observers reported engine sounds, twin engines high and fast, but radar couldn't maintain lock. The contact faded before fighters could intercept. By the time Messerschmitt Bf 109s reached altitude, the intruder had disappeared into darkness over the North Sea. What Richter couldn't know, and what German air defense commanders would struggle to understand for months, was that the British had deployed an aircraft that contradicted everything Luftwaffe intelligence believed about bomber design. A combat plane built almost entirely from wood, so light and aerodynamically clean that it flew over 400 miles per hour, and whose non-metallic construction reflected almost no radar energy, creating natural stealth that German early warning systems couldn't reliably detect. The de Havilland Mosquito had arrived, and Germany's carefully constructed air defense network faced a threat it wasn't designed to counter. The meeting room at the Air Ministry in London felt cold on October 7, 1938. Geoffrey de Havilland sat across a polished table from officials who would decide whether his radical proposal lived or died. At 56 years old, de Havilland had spent 3 decades designing aircraft. He'd founded his company in 1920. He'd built the DH-88 Comet Racer that won the McRobertson Air Race in 1934, flying from England to Australia faster than any aircraft before it. He knew what speed could achieve, but the men across the table didn't want to hear about speed. They wanted bombers that could defend themselves, heavy machine guns and powered turrets, armor plating protecting crews, self-sealing fuel tanks. The doctrine was clear and sensible. Bombers needed defenses because fighters would attack them. Adding guns and armor made aircraft heavier and slower, but protection justified the sacrifice. De Havilland challenged every assumption. His proposal, detailed in drawings spread across the table, showed a twin-engine bomber built almost entirely from wood. No defensive armament, no gun turrets, no armor. The aircraft would rely exclusively on speed and altitude for protection. He estimated it would reach 400 miles per hour, faster than any fighter currently in service. Air Ministry officials were skeptical. Wing Commander Charles Buchanan expressed concerns about wooden construction. Metal was modern. Wood seemed archaic, something from the previous war. And an unarmed bomber contradicted established doctrine developed from hard experience. Bombers without defenses would be slaughtered. De Havilland presented his calculations. A Bristol Blenheim bomber carried crew of 3, defensive guns, ammunition, armor, and bombs. Empty weight approached 10,000 pounds. Add defensive equipment and the weight climbed further, requiring more powerful engines that consumed more fuel, creating spiral where protection reduced performance. His wooden bomber would weigh perhaps 14,000 pounds empty, despite being larger than a Blenheim. Laminated birch plywood and balsa core construction, techniques his company had perfected building racing aircraft, produced structures lighter and stronger than equivalent aluminum. 2 Rolls-Royce Merlin engines would provide exceptional power-to-weight ratio. The result would be aircraft so fast that fighters couldn't catch it. The officials listened but remained unconvinced. Britain faced inevitable war with Germany. The Luftwaffe was expanding rapidly. RAF needed proven designs using proven materials and proven tactics. Wooden bombers without guns seemed desperate rather than innovative. One official noted pointedly that every other nation building modern combat aircraft used metal construction and defensive armament. Perhaps there were good reasons for that consensus. De Havilland persisted through autumn 1938 and into 1939 as war approached. He had one critical advantage. Sir Wilfrid Freeman, Air Council member for Research, Development, and Production, saw potential in unconventional thinking. Freeman recognized that aluminum was scarce. Britain needed every pound of the metal for Spitfires and Hurricanes, but wood was abundant. Furniture craftsmen could build wooden aircraft while metalworkers focused on fighters. The resource argument supported trying de Havilland's approach even if the tactical concept seemed questionable. On September 1, 1939, Germany invaded Poland. 2 days later, Britain declared war. The nation needed aircraft desperately. On December 29, 1939, 4 months into the war, the Air Ministry reluctantly contracted de Havilland to build one prototype. The specification was clear: prove the concept or abandon it. One chance. The contract came with conditions that revealed continued skepticism. The prototype would be tested thoroughly before any production decision. The Air Ministry made no commitments beyond the single experimental aircraft, and if the wooden bomber failed to perform as promised, the program would be canceled immediately. The officials were betting that conventional wisdom would be validated when theories met reality. De Havilland accepted the terms. He'd argued for 2 years that speed could replace guns. Now he had to prove it. His design team, led by Chief Designer R.E. Bishop, relocated to Salisbury Hall near St. Albans for security. They worked in secrecy through winter 1939 and 40, refining drawings, calculating stress loads, designing the manufacturing processes that would turn sketches into flying aircraft. The prototype would test whether wooden construction could survive combat stress, whether speed truly provided adequate defense, whether one engineer's vision could challenge doctrine established by air forces worldwide. But first they had to build it, and building it would require solving problems no one had confronted before. The wooden molds arrived at Salisbury Hall in March 1940. Carved from mahogany, they shaped the fuselage halves, left and right sections that would be joined at centerline. Chief designer R.E. Bishop had developed the construction technique based on methods Arthur Hagg pioneered for the DH-91 Albatross airliner 3 years earlier, but this was combat aircraft, not passenger transport. The structure had to withstand combat stress, high G maneuvers, and battle damage. The sandwich construction began with preparation of the outer skin. Birch plywood from Canada, sheets approximately 4 to 6 millimeters thick, formed the outer and inner layers. Between them, workers placed Ecuadorian balsa wood, precisely 9.5 millimeters thick. The balsa arrived via convoy, running the gauntlet of U-boat attacks in the Atlantic. De Havilland judged the material valuable enough to risk submarine warfare for it. Inside the mahogany molds, workers positioned 7 plywood formers reinforced with spruce blocks. These provided structural framework. Then came the lamination process. Birch plywood outer skin was laid into the mold first. Balsa core followed, cut and fitted precisely to match the fuselage contours. Inner birch plywood skin completed the sandwich. Casein glue, derived from milk proteins, bonded the layers together. Metal clamps held everything tight against the mold, while the adhesive cured under controlled temperature and humidity. The process required days. Workers couldn't rush it. The chemical reaction that hardened casein glue depended on environmental conditions. Too cold and curing slowed. Too warm or humid, and the glue could fail. Salisbury Hall's workshops maintained precise climate control. Approximately 20,000 small brass screws reinforced glue joints in each fuselage half. Another 30,000 secured wing structure. The screws weren't primary structure, the glue was. But the screws provided insurance against adhesive failure and added localized reinforcement at stress points. Each screw was countersunk so it wouldn't protrude above the smooth surface. The fuselage halves emerged from molds as curved shells. Male and female wedge joints lined the edges where the halves would join. But before that final assembly, workers installed internal equipment: wiring, control cables, fuel tanks, instruments. Installing everything after joining the halves would be nearly impossible. The fuselage construction method allowed technicians to work inside each half while it remained open, dramatically simplifying installation. Wing construction followed different but equally sophisticated techniques. The wings were built as single piece spanning wingtip to wingtip with no break at the fuselage. Plywood box spars ran fore and aft, providing primary structure. Plywood ribs and stringers filled gaps between spars. The covering consisted of birch plywood skins, reinforced with birch or Douglas fir stringers glued and screwed between layers. A finished wing could withstand rigorous combat maneuvering at high G loads while carrying thousands of pounds of fuel and weapons. The strength-to-weight ratio equaled or exceeded aluminum construction, and the smooth plywood surface, properly finished, created exceptionally clean aerodynamics without the drag-inducing rivet heads that covered metal aircraft. On November 25, 1940, exactly 1 year after the contract was signed, the prototype Mosquito sat on the airfield at Hatfield. Jeffrey de Havilland's son, also named Jeffrey and the company's chief test pilot, climbed into the cockpit. The yellow-painted prototype designated E0234 carried two Rolls-Royce Merlin 21 engines. Empty weight was 14,300 pounds, remarkably light for an aircraft of its size. De Havilland Jr. started engines, conducted pre-flight checks, and advanced throttles. The Mosquito accelerated down the runway and lifted off smoothly. The test flight lasted approximately 30 minutes. De Havilland tested handling, control response, and basic performance. When he landed and taxied back, his report was unambiguous. The aircraft exceeded expectations. It was fast, maneuverable, and structurally sound. Subsequent test flights expanded the performance envelope. On February 19, 1941, the prototype reached 388 miles per hour at 22,000 feet, faster than the Spitfire Mk2 then entering service. With improvements, de Havilland estimated operational Mosquitoes would exceed 400 miles. The wooden aircraft was legitimately faster than contemporary fighters. The wooden construction offered unexpected advantages beyond just performance. Damage repairs could be accomplished using available materials and skilled furniture workers rather than specialized metal workers and scarce aluminum. Piano factories, furniture manufacturers, and cabinet makers across Britain had skilled craftsmen whose expertise wasn't being utilized for war production. The Mosquito could employ them. De Havilland dispersed component manufacturing to workshops around High Wycombe in Buckinghamshire, where furniture factories and piano manufacturers produced fuselage sections, wing panels, and structural components. A fuselage could be equipped by 6 workers in a week. The only major metal parts were radiators, engine mounts, and undercarriage. Even ailerons initially framed in aluminum were eventually redesigned in wood. On March 3, 1941, government test pilots conducting official trials published favorable report on the prototype. Official doubt turned to quiet confidence. The Air Ministry placed production order on June 21, 1941. 19 photo reconnaissance aircraft, 176 fighters, and 50 bombers. Additional contracts followed. Eventually, production would reach 7,881 aircraft in 36 variants built in Britain, Canada, and Australia. But questions remained. The prototype had proven the concept under controlled test conditions. Combat would be different. Could wooden structure survive battle damage from cannon shells and machine gun fire? Would the case and glue hold at extreme altitudes where temperatures drop to minus 40 degrees Celsius? Would sustained operations reveal structural weaknesses that limited testing hadn't exposed? The Mosquito's true test would come not in test flights over England, but in operations over Germany, where Luftwaffe fighters and flak batteries would determine whether Jeffrey de Havilland's wooden wonder could survive the war it was designed to fight. Squadron leader Charles Patterson sat in the briefing room at RAF Horsham St. Faith on September 17, 1941. His aircraft, Mosquito PR-MAKI serial number W405FEV, sat outside, pale blue camouflage gleaming in morning light. The mission was reconnaissance over France. No fighter escort, no defensive guns, just speed. Patterson and Navigator Flight Lieutenant Lawson would fly at 23,000 feet, photographing German installations. If intercepted, they would run. The Mosquito carried cameras where bombers carried guns. Air Ministry planners believed 380 mm would protect the crew better than machine guns ever could. Patterson was about to test whether that theory survived contact with the Luftwaffe. The Mosquito climbed smoothly to altitude over the English Channel. Patterson leveled off at 23,000 feet and turned toward France. The Merlin 21 engines ran cleanly, pulling the wooden aircraft through thin air at cruising speed. Below, the French coast passed. Ahead lay the reconnaissance targets. Then Lawson spotted them. 3 Messerschmitt Bf-109s climbing from below, vectored by German radar toward the intruder. The fighters were at 20,000 feet and climbing. Patterson had altitude advantage, but the 109s were fast. Top speed around 357 mph at their optimal altitude. The gap was narrow. Patterson didn't wait to see if they'd catch up. He pushed throttles forward and the Mosquito accelerated. The wooden airframe's smooth plywood skin created minimal drag. The Merlin engines delivered 1,560 horsepower combined. The aircraft surged ahead, pulling away from the climbing 109s. Patterson held speed at 300 mph, watching the German fighters fall, behind. They couldn't match his altitude and speed combination. After 10 minutes, the Messerschmitts gave up and turned away. Patterson completed his reconnaissance run, photographed the targets, and returned to England. The mission report confirmed what test flights had suggested. The Mosquito was legitimately faster than fighters trying to intercept it. Defensive armament wasn't necessary when the aircraft simply outran threats. On November 15, 1941, 105 Squadron took delivery of the first operational Mosquito BMKV bomber, serial number W4064. The bomber variant carried 2,000 pounds of bombs, where photo reconnaissance aircraft carried cameras. It retained the speed but added offensive capability. Squadron leader Huey Edwards commanded 105 Squadron. His crews faced skepticism from other bomber units flying Wellingtons and Blenheims with multiple gun turrets. An unarmed bomber seemed suicidal. The first operational bomber mission came on May 31, 1942. 4 Mosquitoes from 105 Squadron attacked Cologne in daylight. The same night, RAF launched its first 1,000 bomber raid on the city. The Mosquitoes reached target, dropped bombs, and returned without loss. Speed had protected them exactly as de Havilland predicted. Operations expanded through summer and autumn 1942. Mosquito crews flew daylight raids against industrial targets in occupied Europe. Factories, power stations, railways. The tactics were audacious. Mosquitoes attacked in formations of 6 to 12 aircraft, flying at low level to avoid radar detection, then climbing rapidly to bombing altitude, striking targets, and accelerating away before German fighters could respond effectively. On September 25, 1942, 105 Squadron conducted precision raid on Gestapo headquarters in Oslo, Norway. 4 Mosquitoes flew 100 miles round trip, attacked the target building at low altitude, and returned to England. The mission demonstrated the aircraft's versatility. Fast enough for daylight operations, maneuverable enough for precision attacks, with range-enabling strikes against distant targets. But it was the Berlin raid that validated the Mosquito's strategic value. On January 30, 1943, the 10th anniversary of Hitler becoming Chancellor, 105 Squadron launched morning raid on Berlin. 3 Mosquitoes flew at 25,000 feet, reaching the German capital in daylight. They bombed Berlin Broadcasting Station while Hermann Göring was delivering anniversary speech, knocking the transmission off the air. The Mosquitoes escaped before German fighters could intercept. The performance statistics exceeded contemporary fighters. The Mosquito BMK-4 achieved 380 mph at 17,000 feet. Maximum speed topped 400 mph at optimal altitude. By comparison, Messerschmitt Bf-109F-4 fighters, the standard Luftwaffe interceptor in 1942, achieved maximum 388 mph at 22,000 feet. The wooden bomber matched or exceeded fighter performance. Focke-Wulf FW-190A. Fighters introduced in 1941 were faster than Bf-109s, reaching 4 km at 2,600 feet. But Mosquitoes operating at 25,000 feet flew above the FW-190's optimal altitude, where German fighter performance degraded. And Mosquito pilots flying at maximum continuous power could sustain speeds German fighters could only achieve in short sprint. Loss rates proved de Havilland's concept. Heavy bombers, Lancasters, Halifaxes, Wellingtons, faced loss rates approaching 5% per mission during 1942-43. Mosquito squadrons recorded loss rates below 2%. The unarmed wooden bomber survived better than heavily armed metal bombers because speed prevented interception more effectively than defensive guns deterred attacks. The aircraft demonstrated that unconventional thinking could create strategic advantage. By rejecting established doctrine about defensive armament, de Havilland created bomber that relied on performance rather than firepower for survival. Air Ministry officials who'd been skeptical in 1938 now praised the design. Orders increased. Production expanded beyond de Havilland to subcontractors across Britain, Canada, and Australia. But Luftwaffe was adapting. German fighter units developed tactics specifically for intercepting mosquitoes. Diving attacks from superior altitude, coordinated interceptions using radar-directed fighters positioned along known flight paths, concentration of faster FW-190 units near likely targets. And German technical intelligence services studied crashed mosquitoes, analyzing the wooden construction to understand how British engineers had achieved such performance from unconventional materials. The advantage wouldn't last forever unchallenged, and as 1943 progressed into 1944, the wooden wonder would face increasingly sophisticated German countertactics designed specifically to bring down the aircraft that seemed impossible to catch. The Würzburg radar station near Emden operated throughout January 1943, tracking RAF bombers crossing German airspace. Obergefreiter Klaus Richter and his fellow operators had worked the equipment for 18 months. They understood its capabilities and limitations. The Würzburg D model used conical scanning to achieve remarkable accuracy, 0.2 degrees in azimuth, 0.3 degrees in elevation. Its 3-meter diameter parabolic dish transmitted pulses at 560 MHz, bouncing radio waves off metal aircraft at ranges approaching 40 kilometers. The system worked by detecting reflected radio energy. Metal aircraft structures, aluminum airframes, steel components, engine blocks, reflected radio waves back toward the radar receiver. The stronger the return signal, the clearer the target appeared on the oscilloscope display. Lancasters and Halifaxes painted bright returns. Their all-metal construction created large radar cross-sections that German operators tracked reliably from first detection until handoff to night fighters or flak batteries. But mosquitoes presented different challenge. Richter first encountered the phenomenon in late 1942. Contact would appear on his display, weak, flickering, moving faster than typical bombers. He'd attempt to establish tracking, but the return faded and reappeared irregularly. Sometimes he maintained lock long enough to vector fighters. Often the contact disappeared entirely despite ground observers reporting engine sounds overhead. The technical explanation lay in materials science rather than radar technology. The Würzburg's radio pulses reflected off metal surfaces. Birch plywood and balsa wood absorbed or transmitted most radio energy rather than reflecting it. The mosquito's wooden construction contained minimal metal components. 2 Rolls-Royce Merlin engines provided the largest metal masses, approximately 1/400 pounds of aluminum, steel, and copper per engine. Control cables, instruments, landing gear, fuel tanks, and various fittings added perhaps another 1,500 pounds of metal total. By comparison, an Avro Lancaster bomber contained over 25,000 pounds of aluminum airframe structure, plus engines, guns, turrets, ammunition, and equipment. The Lancaster presented radar cross-section perhaps 10 times larger than a mosquito. Würzburg operators tracking Lancaster saw strong, steady returns. Mosquitoes appeared as weak, intermittent contacts barely distinguishable from atmospheric noise. The stealth effect wasn't absolute. Under ideal conditions, mosquito flying directly toward or away from radar, minimal atmospheric interference, experienced operator. Würzburg could detect and track wooden aircraft. But combat operations rarely provided ideal conditions. Mosquitoes typically approached at angles that minimized radar reflection. Atmospheric conditions varied, and operators managing multiple contacts simultaneously couldn't devote exclusive attention to weak, flickering returns that appeared and disappeared. The combination of weak radar signature and high speed created tactical advantage German air defense struggled to counter. Even when Würzburg detected a mosquito, maintaining tracking long enough to vector fighters required continuous lock. The weak return made that difficult. If the operator lost contact for even 30 seconds, the fast-moving mosquito could be miles from its last known position when radar reacquired it, if reacquisition happened at all. German fighter tactics depended on ground-controlled interception. The Kammhuber Line air defense system used Freya early warning radars to detect incoming bombers at long range, then handed off to Würzburg tracking radars that guided Messerschmitt Bf 110 or Junkers Ju-88 night fighters toward targets. The system worked brilliantly against heavy bomber streams flying predictable courses at steady speeds. Controllers could vector fighters to interception points with confidence, but Mosquitoes defeated the system by breaking its fundamental assumptions. The weak radar return prevented reliable tracking. The high speed meant interception calculations became obsolete within minutes, and Mosquito operations, small formations, irregular routing, rapid strikes, didn't provide the sustained tracking opportunities that heavy bomber streams offered. The accidental stealth demonstrated how materials choices created military advantages designers hadn't explicitly intended. Geoffrey de Havilland selected wooden construction for weight savings, manufacturing simplicity, and aluminum conservation. He understood that lightweight airframe would enable high performance, but he hadn't calculated that non-metallic structure would also reduce radar detectability. The stealth was an unintended consequence of engineering decisions made for entirely different reasons. British intelligence gradually recognized the phenomenon. RAF Signals Intelligence monitoring German radar emissions noted that Mosquito operations generated fewer tracking contacts than equivalent numbers of metal aircraft. Captured Luftwaffe radar operators described difficulties tracking fast-moving targets with weak returns. By mid-1943, British planners understood that Mosquitoes possessed inherent radar evasion capability beyond just speed. The knowledge influenced tactics. Mosquito squadrons began exploiting the stealth advantage deliberately. Crews flew routes designed to minimize radar exposure, approaching targets from angles that reduced reflection, using terrain masking when possible, varying altitudes to complicate tracking. The combination of natural stealth and tactical employment made interception increasingly difficult. But Luftwaffe was adapting. German radar engineers developed improved detection methods. Freya early warning radars operating at lower frequencies could detect wooden aircraft more reliably than Würzburg's higher frequency pulses. Multiple radar stations operating in overlapping coverage could maintain tracking even when individual units lost contact. And Luftwaffe fighter units developed tactics specifically for intercepting Mosquitoes, positioning faster Focke-Wulf FW-190 and Messerschmitt Mi-262. Jet fighters along known flight paths, using altitude advantages to dive on targets before they could accelerate away, concentrating defenses around high-value targets where Mosquitoes were most likely to appear. The wooden construction that created accidental stealth also limited how far the advantage could be exploited. Unlike deliberate stealth aircraft designed decades later, with radar-absorbing materials and carefully shaped surfaces, the Mosquito's stealth was byproduct of using available materials for their mechanical rather than electronic properties. The advantage existed, but remained vulnerable to improved detection technology and evolved tactics designed specifically to counter it. As 1943 became 1944, Luftwaffe countermeasures would increasingly challenge the Mosquito's combination of speed and stealth, forcing RAF to continuously adapt operations to maintain the edge that wooden construction and brilliant engineering had created. Reichsmarschall Hermann Göring sat in his office at Luftwaffe headquarters on March 12, 1943, reading reconnaissance reports that made him increasingly angry. British aircraft had photographed Berlin 3 times in the past week. All 3 missions were flown in daylight. The bombers, if they could be called bombers given their minuscule bomb loads, flew too fast for fighters to intercept and too high for flak to reach effectively. German air defenses protecting the Reich capital had failed to stop a single wooden British aircraft. Göring's frustration reflected broader Luftwaffe problems with Mosquito operations. The aircraft violated every assumption German air defense doctrine was built upon. Heavy bombers flew in formations for mutual defense. Mosquitoes operated alone or in small groups. Bombers needed fighter escorts. Mosquitoes flew unescorted. Bombers could be intercepted with proper radar vectoring and fighter positioning. Mosquitoes disappeared before fighters reached altitude. The tactical mathematics favored the British. A Messerschmitt Bf-109G6 fighter, standard Luftwaffe interceptor in 1943, achieved maximum speed of 386 miles per hour at 22,800 feet. But reaching that altitude from ground level required 12 to 13 minutes of climbing. A Mosquito detected at 25,000 feet, cruising at 370 miles per hour could cover 70 miles in those 13 minutes. By the time the Bf-109 reached intercept altitude, the Mosquito had struck its target and was fleeing at maximum speed exceeding 400 miles per hour. Focke-Wulf FW-190A fighters performed slightly better. The FW-190A8 variant, introduced in late 1943, achieved 408 mm at 2,600 feet, theoretically fast enough to catch mosquitoes. But the performance advantage only existed at specific altitudes. Mosquitoes operating above 25,000 feet flew faster than FW-190s could climb. And even when German fighters achieved advantageous positioning, they had narrow windows to engage before mosquitoes accelerated away. Luftwaffe fighter tactics evolved trying to counter the wooden threat. Jagdgeschwader JG-25 and JG-50 stationed fighters at high altitude on standing patrol along likely mosquito routes. The tactic occasionally worked. Positioning fighters already at 30,000 feet allowed diving attacks that closed speed differential. But maintaining standing patrols consumed enormous fuel and achieved interceptions rarely enough that resources expended vastly exceeded results achieved. German pilots who did engage mosquitoes reported frustrating encounters. Oberleutnant Heinz Knoke of JG-1 described chasing a mosquito over Bremen in April 1943. He'd achieved altitude advantage and dove at maximum speed. His FW-190 briefly closed the gap. But before he could fire effectively, the mosquito pilot saw him, pushed throttles forward, and accelerated away. Knoke's fighter couldn't match the sustained high-speed performance. The engagement lasted perhaps 90 seconds before the mosquito disappeared. Flak batteries faced similar frustration. The 8.8 cm flak guns protecting German cities could reach 32,000 feet theoretically, but engaging targets above 25,000 feet moving at 400 mm required firing solutions that consumed ammunition wastefully. Mosquitoes flew too high and too fast for effective anti-aircraft fire. Gun crews fired thousands of shells at fleeting targets with minimal success. The psychological impact exceeded the mosquito's tactical role. RAF bomber streams attacking at night caused massive destruction and casualties. But German civilians and military personnel accepted night bombing as inevitable consequence of total war. Daylight mosquito raids over Berlin and other major cities demonstrated something more unsettling. German air defenses couldn't guarantee protection even in daytime, even over the capital, even against small numbers of British aircraft. The phenomenon created what German night fighter crews called Moskitoschreck, mosquito terror. RAF Mosquito night fighters began intruder operations over Luftwaffe airfields in mid-1942, attacking German aircraft during the landing approaches when they were most vulnerable. Pilots flying night missions returned to base exhausted, focused on landing safely, navigation lights illuminated to avoid collisions. Then mosquitoes appeared from darkness, machine guns and cannon firing. Dozens of German night fighters were destroyed during landing patterns. The intruder threat forced Luftwaffe to implement costly countermeasures. Fighters landing at night now approached with lights off until final moments. Airfield defenses were strengthened. Landing schedules were varied to prevent predictability. All measures consumed resources and complicated operations that should have been routine. The mosquito's mere presence over German airfields created disproportionate disruption. Göring's reported comment about the mosquito being a damned nuisance understated German frustration. The aircraft represented a strategic problem with no easy solution. Intercepting mosquitoes required faster fighters, but developing, testing, and producing new fighters required time and resources Germany couldn't spare while fighting on multiple fronts. Improving radar couldn't overcome the wooden airframe's minimal reflection. Enhanced flak defenses couldn't reach high-altitude targets effectively. By late 1943, Luftwaffe recognized that conventional countermeasures weren't working. Germany began developing jet-powered fighters specifically capable of catching mosquitoes. The Messerschmitt Me-262 achieved 540 km/h, fast enough to intercept any piston-engine aircraft. Development accelerated through 1944, driven partly by recognition that existing fighters couldn't counter the wooden wonder. But jet fighter development faced Hitler's interference. The Führer insisted Me-262 be developed as fighter bomber rather than pure interceptor, delaying operational deployment. Fuel shortages constrained training and operations. Allied bombing disrupted production facilities. The technological solution arrived too late and in insufficient numbers to matter strategically. On July 25, 1944, Lieutenant Alfred Schreiber, flying Me-262, A-1A intercepted Mosquito PR MAK 6th MM273 over Munich. The jet fighter made 6 passes attempting to destroy the wooden aircraft. The Mosquito crew, Flight Lieutenant A.E. Wall and Flying Officer A.S. Laban, executed violent evasive maneuvers and escaped into clouds, making emergency landing in Italy. The encounter demonstrated that jets could engage mosquitoes successfully, but isolated interceptions couldn't change strategic reality. Germany lacked fuel, pilots, and production capacity to deploy jet fighters in numbers that would neutralize the mosquito threat. Through 1944 into 1945, Mosquitoes continued operations with loss rates below 2%, dramatically lower than heavy bombers. The wooden aircraft that Göring called a nuisance remained problem Luftwaffe never solved. Resources dedicated to countering Mosquitoes, standing fighter patrols, enhanced radar networks, jet fighter development, consumed capacity Germany needed for defending against heavy bomber streams and supporting ground forces collapsing on eastern and western fronts. The Mosquito's strategic impact came not from the tonnage of bombs it dropped, but from forcing Germany to dedicate disproportionate resources, trying unsuccessfully to counter a single aircraft design that shouldn't have worked but did. The Mosquito FB MK that Wing Commander Bob Braham flew on June 17, 1944, bore little resemblance to the unarmed bomber Jeffrey de Havilland had originally proposed. The fighter-bomber variant carried 4 20mm Hispano cannons in the belly, 4 .303 machine guns in the nose, and 2 500-pound bombs in a small internal bay. Braham's aircraft, designated MM-403, also mounted 8 RP-3 rocket projectiles under the wings. This single wooden airframe combined roles that typically required 3 different aircraft types. The versatility stemmed from de Havilland's clean, high-performance basic design. The wooden monocoque fuselage could accommodate different equipment without major structural changes. The nose section was modular, solid for fighters, glazed for bombers, equipped with cameras for reconnaissance. Wing hardpoints supported bombs, rockets, or fuel tanks. The basic airframe remained essentially unchanged, while mission equipment varied dramatically. By 1944, over 30 distinct Mosquito variants served with RAF and Allied forces. The BMK IFA bomber carried 2,000 pounds of bombs internally at 300 km/h. The PRMK Eskistarn photo reconnaissance aircraft flew at 425 km/h with cameras replacing weapons. The NF MK-3 night fighter carried AI Mekal 8 radar in a solid nose thimble, 4 cannons, and Merlin 21 or 23 engines. The FB Mekal 6 fighter bomber combined guns, bombs, and rockets for ground attack and anti-shipping strikes. Production statistics revealed the design's strategic value. Total, Mosquito production reached 7,781 aircraft. British factories built 6,710 during wartime, including 309 at Hatfield, 1,006 at Leavesden, and 1,066 by Standard Motors. De Havilland Canada produced 1,133 aircraft in Toronto. De Havilland Australia built 212 at Bankstown. The FB MKS fighter bomber alone accounted for 2,584 aircraft, the single most produced variant reflecting its versatility. The wooden construction enabled dispersed production using furniture industry infrastructure. Piano factories in High Wycombe manufactured fuselage sections. Cabinet makers produced wing components. Craftsmen who'd built dining tables now assembled aircraft structures using techniques they already understood. The production network allowed Britain to build thousands of combat aircraft without consuming scarce aluminum or occupying specialized aircraft factories needed for Spitfires and Lancasters. Mission versatility multiplied the Mosquito's strategic impact beyond its numbers. On February 18, 1944, 18 Mosquito FB-MKCs from 140 Wing attacked Amiens prison in Operation Jericho, breaching walls to allow resistance prisoners to escape. The precision low-level strike demonstrated capabilities no heavy bomber possessed. 3 Mosquitoes were lost, but approximately 250 prisoners escaped, though many were quickly recaptured. Night fighter variants transformed RAF's defensive capabilities. The Mosquito NF Mk2 entered service in May 1942, equipped with AI Mk4 radar. Crews hunted German bombers over Britain and later conducted intruder missions over occupied Europe. Wing Commander Braham, RAF's top-scoring night fighter ace, credited the Mosquito's speed and radar with enabling his 29 victories. German bombers couldn't outrun Mosquito interceptors, and the wooden construction's relative quiet gave defenders tactical advantage over noisy German aircraft. Pathfinder Force used Mosquito bomber variants to mark targets for heavy bomber streams. The aircraft's speed and altitude performance allowed it to reach targets first, drop target indicators, and depart before German defenses could respond effectively. By December 1943, Mosquitoes equipped the Light Night Striking Force, elite unit conducting precision raids on Berlin and other German cities while heavy bombers struck elsewhere, dividing German defenses. Maritime strike variants attacked German shipping and U-boats. The FB MIKS Unikit Tsetse mounted a 57mm Molins automatic cannon, essentially a 6-pounder anti-tank gun, in the nose for attacking submarines and surface vessels. The weapon's recoil generated forces the wooden airframe absorbed surprisingly well. 27 Tsetse variants served with 248 Squadron, sinking multiple U-boats in Bay of Biscay operations. Training variants prepared crews for operational flying. The TMK-3 trainer featured dual controls and was used to convert pilots to Mosquito operations. Some bombers and fighters were retrofitted as trainers after completing operational service. The wooden construction's durability meant airframes withstood training stresses that destroyed more fragile aircraft. Post-war variants continued the evolution. The BMK-35, introduced in 1945, featured uprated Merlin 114 engines producing 1,110 horsepower each and GH radio navigation system. Though arriving too late for wartime service, the variant demonstrated continued development potential. Some BMK-35 served with RAF until 1953, over a decade after the original bomber variant entered service. The versatility validated de Havilland's fundamental design philosophy. By creating clean, high-performance airframe uncompromised by defensive armament or specialized equipment, he'd produced platform adaptable to evolving needs. The modular nose, accessible internal volume, and excellent performance characteristics enabled modifications that would have been impossible with purpose-built aircraft constrained by original design assumptions. But versatility came at cost, measured in human lives rather than tactical effectiveness. Mosquito crews flew alone or in small formations, often at night, deep into enemy territory. No fighter escort protected them. No formation provided mutual defense. Speed and skill were their only shields against overwhelming defensive firepower. When mechanical failures occurred or battle damage accumulated, crews had no backup. They either reached friendly territory or they died. Squadron losses tell the human story behind strategic success. 105 Squadron, first to operate Mosquito bombers operationally, lost 87 aircraft between May 1942 and war's end. Some crews completed tours successfully. Others died on first missions. The wooden wonder that seemed invulnerable to German defenses could still be destroyed by flak, fighters, mechanical failure, or pilot error. And because missions were flown alone when Mosquitoes didn't return, often no one knew what happened. The 7,781 Mosquitoes built represented more than production statistics. Each airframe symbolized Britain's ability to innovate under pressure, adapt existing resources creatively, and produce weapons that exceeded what conventional thinking suggested was possible. The versatility demonstrated that one brilliant design could serve countless roles more effectively than multiple specialized aircraft, proving sometimes the best solution was platforms simple enough to adapt, but sophisticated enough to excel at whatever mission circumstance demanded. 75 years after Klaus Richter watched the flickering radar return disappear over Emden, aviation historians examining World War II's most influential aircraft designs recognize the de Havilland Mosquito as one of the war's most remarkable achievements, not because it represented cutting-edge technology, but because it challenged fundamental assumptions about how combat aircraft should be designed. The Mosquito succeeded by systematically rejecting conventional wisdom. It used woodens, construction when metal was standard. It eliminated defensive armament when heavy guns seemed essential. It relied on speed and altitude when armor appeared necessary. Each unconventional choice contributed to creating aircraft that outperformed more sophisticated designs. American aircraft manufacturers had dismissed the concept when shown de Havilland's drawings in 1941. Beech Aircraft's evaluation concluded, It appears as though this airplane has sacrificed serviceability, structural strength, ease of construction, and flying characteristics in an attempt to use construction material which is not suitable for the manufacture of efficient airplanes. The assessment reflected consensus thinking about modern combat aircraft design. Wood was obsolete, metal was modern. The Americans recommended building Lockheed P-38 Lightnings instead. But the American evaluation missed what made the Mosquito revolutionary. De Havilland hadn't chosen wood despite its obsolescence. He'd exploited wood because of advantages metal couldn't match. Wooden construction was lighter. It could be manufactured using furniture industry infrastructure. It required no scarce aluminum. And accidentally, it reflected minimal radar energy. The wooden wonder validated principle that constraints drive innovation. Wartime aluminum shortages and need for production, using existing manufacturing capability forced de Havilland to work with available materials. Those constraints produced advantages deliberate design might not have discovered. The limitations became strengths when engineer understood materials well enough to exploit their properties rather than compensating for their weaknesses. The broader lesson extended beyond material science. The Mosquito succeeded because Geoffrey de Havilland questioned established doctrine rather than incrementally improving existing approaches. RAF doctrine emphasized defensive armament. De Havilland eliminated it. Doctrine required bombers fly in formations for mutual defense. The Mosquito operated alone. Doctrine assumed heavier meant more survivable. De Havilland proved lighter could be better. Each decision contradicted expert consensus. Air Ministry officials were skeptical. Competing manufacturers dismissed the concept. American evaluators recommended against it. But de Havilland understood that breakthrough innovations came from challenging assumptions rather than refining existing solutions. The wooden bomber succeeded precisely because it defied expectations about what combat aircraft should be. The legacy influenced post-war aviation development. The Mosquito's composite sandwich construction, plywood skins bonded to balsa cores, pioneered techniques that evolved into modern composite materials. Today's carbon fiber airframes use fundamentally similar principles. Lightweight cores sandwiched between strong skins, adhesive bonding replacing mechanical fasteners, tailored construction optimizing strength-to-weight ratios. The wooden. Construction methods furniture craftsmen perfected in 1940s workshops informed aerospace engineering decades later. The aircraft's performance characteristics influenced jet bomber design. The English electric Canberra that replaced the Mosquito in 1951 adopted similar philosophy: fast, high-altitude, minimal defensive armament. The Canberra relied on performance for protection, just as the Mosquito had. The concept endured because the Mosquito proved it worked. Modern stealth aircraft represent parallel evolution. The Mosquito's accidental radar transparency, wooden construction reflecting minimal electromagnetic energy, foreshadowed deliberate stealth technology developed 40 years later. The F-117 Nighthawk and B-2 Spirit achieved through design what the Mosquito accomplished through materials: reduced radar cross-section creating survivability advantage. The principle was identical, even though implementation differed dramatically. The lesson endures in contemporary aerospace development, where unmanned systems challenge assumptions about requiring pilots aboard, where composite materials replace metals, where distributed propulsion questions conventional engine placement. Each innovation faces skepticism similar to what de Havilland encountered. Each succeeds by demonstrating that different doesn't mean inferior, just different enough to create advantages conventional designs can't match. The Mosquito's story revealed deeper truth about military innovation. Breakthrough designs emerged not from incremental refinement, but from fundamental rethinking. When Geoffrey de Havilland proposed building fast bomber from wood, he wasn't suggesting minor modification to existing aircraft. He was questioning whether established doctrine about defensive armament, metal construction, and formation tactics actually served strategic objectives or simply reflected institutional inertia. The answer proved that doctrine often lagged behind technological possibility. The Mosquito demonstrated that single aircraft could outperform specialized designs by being simple enough to adapt, but sophisticated enough to excel. The wooden construction that seemed archaic enabled versatility metal airframes couldn't match. The lack of defensive guns that seemed suicidal enabled speed that made interception nearly impossible. By 1945, when the last Mosquito left production lines, 7,781 aircraft had been built. They'd flown every role RAF needed: bomber, fighter, reconnaissance, pathfinder, intruder, maritime strike, trainer. Loss rates below 2% validated design philosophy that seemed radical when proposed 6 years earlier. The Wooden Wonder had proven skeptics wrong through operational success that theory alone couldn't achieve. Geoffrey de Havilland died in 1965, having witnessed his wooden bomber's vindication and influence on subsequent aviation development. His son, the test pilot who had first flown the prototype, had died in 1946 testing experimental aircraft, but the principle both embodied and endured: that innovation came from questioning assumptions, that constraints could drive creativity, and that sometimes the best solution was the one everyone said wouldn't work until someone built it and proved otherwise. The Mosquito's legacy wasn't just 7,781 aircraft or missions flown or targets destroyed. It was demonstration that military effectiveness derived not from following established patterns, but from recognizing when those patterns no longer served strategic needs. The wooden aircraft that Germany laughed at, until it flew too fast for radar to track, too high for fighters to catch, and too successfully for doctrine to explain, remained proof that sometimes the impossible was just the conventional waiting to be challenged by someone willing to try.